The materials in this video corresponds to section 9.8 on your textbook. I'm going to talk about another algorithm which can also be used to solve integer programming problems. It's called the cutting plane algorithm. We are going to use the example 9 of Telfa Corporation, who is producing tables and chairs, and then both variables, the number of tables and the number of chairs that are manufactured, both must be integer. And we have the labor constraint and wood constraint, and then what we're going to do in this problem is maximizing the profit. As usual, we start with solving the LP relaxation of the integer programming problem. So let's say we are solving the problem using Simplex algorithm, and this is the optimal table. So remember to read this optimal table is that z equals to 41.25 here, and then x2 equals to 2.25, and then x1 equals to 3.75. That's how to read the optimal table. And then the cutting plane algorithm will start by picking the constraint in the table whose right-hand side is fractional. So we have two constraints here whose right-hand side are both fractional. And then it suggests us, the algorithm suggests us to pick the one closest to 0.5. Means the decimal is closest to 0.5. However, here the decimals are 0.25 and 0.75. Both are equally close to 0.5. So we can just pick any of them. Okay. So here in this case, the book picked the second constraint to be solved by the cutting plane algorithm. Now, this is the second constraint that we pick from the table. So from the table, we can say that the second constraint or the second row can also be written into this form. Okay, if you're not sure, take a look back at the table and then see that we simply change the numbers with the variables. So 1 times x1 minus 1.25 times s1 plus 0.25 times s2 equals the right-hand side 3.75. So that was the second constraint. And then what we're going to do is that we're going to first define this x in a bracket to be the largest integer less than or equal to x. So if x is a number, x in a bracket means the largest integer less than or equal to x. What we're going to do with this x in the bracket is that we're going to write down all coefficients and the right-hand side in the form of x in the bracket plus f. What does this mean? It means that now let's see, we're translating from that second constraint, translating from that second constraint in the optimal table into this form. So let's start. 1 times x1. 1 is already integer, so we do nothing. And then here we see that we have minus 125. Now ask yourself, what is the largest integer, but it is less than minus 1.25? The answer is minus 2. Because minus 2 is the largest possible integer that is still less than minus 125. Okay, so all the integers that are less than or equal to minus 125 are minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, and so on. Among all those integers, we pick the largest one, which is minus 2. So we write down minus 25 as minus 2 plus 0.75. Okay, so let me repeat. The original coefficient is minus 125, minus 1.25. Now think about all the integers that are less than minus 1.25. Minus 2, minus 3, minus 4, minus 5, and so on. They are all less than minus 125. Now among all those numbers, pick the largest one, which is minus 2. Now you write down minus 125 as minus 2 plus 0.75. Now what about 0.25? Again, try the same thing. What are the integers that are less than or equal to 0.25? Less than or equal to 0.25. It means 0, minus 1, minus 2, minus 3, minus 4, and so on. Among all those numbers, pick one which is the largest among them. Okay, so the answer is 0. So you rewrite 0.25 as 0 plus 0.25 here. Now what about 3.75? Again, start by thinking, what are the integers that are less than or equal to 3.75? Well, less than or equal to 3.75 integers. It means 3, 2, 1, 0, minus 1, minus 2, minus 3, and so on. Now among all those numbers, again, pick the largest one. The largest one is 3. So now we are rewriting 3.75 to become 3 plus 0.75. Okay, this can be a bit tricky, but always think about what are the integers that are less than or equal to that number. You list all those integers and then pick one which is the largest among them. Then rewrite the original non-integers in the form of this integer x in the bracket plus f. And then f must be between 0 or less than 1. Now we put all terms with the integer coefficients on the left-hand side and all terms with fractional coefficients on the right-hand side. So you put all the variables with the integer coefficients on the left, and then you move anything that is fractional to the right-hand side. Sorry, this 0.75 is this. This is the 0.25. Then from here, you get that one. I know it's a bit messy, but the idea is that anything with integer coefficients, you push them to the left-hand side. Anything with the fractional coefficients, you push it to the right-hand side. And what about 0? 0 belongs to the left-hand side. Okay, so up to this step, that's what we've been doing. All integer coefficients on the left, all non-integer coefficients on the right. Now, once we have arranged the constraint into such form, integer coefficients on the left, non-integer coefficients on the right, the cutting plane algorithm is actually very simple. It just says that now we're adding one constraint saying that this right-hand side must be less than or equals to 0. So now you adding one constraint, which is called the cut constraint to your problem, which is on this right-hand side. So you just put it here, must be less than or equals to 0. Okay, and then from this line to the next line, you just rearrange the numbers. such that 0.75 here goes to the right hand side. Now this is the constraint that we are adding to our problem, and it is called the cut constraint. Once we have that constraint, we can, as usual, convert it into standard form by adding a slack variable. Remember, because the sign is less than or equal to, so you are adding a slack variable. Let's call it S3. And then we append that constraint, that cut constraint, into the old optimal table. So we had an optimal table before, we had this cut constraint, you have converted this constraint into standard form by adding S3. Now you're ready to put this new constraint into that old table. Let's see how we can do that. So the first, this is row 0, row 1, and row 2 are exactly the same as the optimal table from the Simplex that we have seen before, so nothing changes. Now this row 3 here is the cut constraint that we have converted into standard form. So you see there's a new variable S3 here because we are converting this cut constraint into standard form. So this is our cut constraint, and then we are resolving this table to get the new optimal solution. How can we do that? Remember, when you're adding a constraint like this, it is easier to solve this problem using dual simplex. Okay, so dual simplex, basically you just pick the most negative right-hand side, and then you check the ratio test for all the variables with negative coefficients, and then pick one with the absolute value ratio test, with the smallest absolute value of ratio test. And then here, so this variable has the smallest absolute value of ratio test. So then now it should become 1, and the other value on that column should become 0. And then you perform the elementary row operation to make it happen, and then see if this new solution is optimal. For the maximization problem, if this row 0 is already all positive coefficients, means it's already optimal. We may also visualize how cutting plane works, because the previous problems has only 2 variables, so we can see how this cutting plane actually looks like in the 2D graph. So let's go back to the original problem. So this is the original formulation, and then whenever we do the simplex algorithm, we always convert the constraints into standard form. So now the first constraint you're adding S1, slack 1, and then such that you may define S1 is 6 minus X1 minus X2. So 6 is from the right hand side, and then minus X1 minus X2 is because we are moving them from left hand side to right hand side. Okay, and then the second constraint also, because the sign is less than or equals to, we are going to add S2 to make it equal, and then we just move everything to the right hand side. So now you have the definition of S2 equals 45 minus 9x1 minus 5x2. Now this is the cut constraint that we have on the previous 2 slides, I think. So how can we draw that cut constraint in this graph? Because the axis of this graph is x1 and x2, so we must convert s1, s2 into x1 and x2. Well, we've got the definition of s1 here and s2 there, so you just plug those numbers in. You may try this. Actually, I strongly suggest you to really try to plug in the numbers and prove that yes, actually if you convert S1, S2 according to this equations, you will get this equation here. Okay, now because the variables are 3x1 and 2x2 less than or equals to 15, you may draw that cutting plane, which is this line here. So that line is the cutting plane. What does it cut actually, and why is it named the cut constraint? Well, if you really notice this cut constraint, it cuts out the optimal solution to the LP relaxation. See, this point is outside of the cutting plane because the cutting plane sign is less than or equals to, so it will be, the feasible region will be this area. What does that mean? It means that the optimal solution to the LP relaxations, which is not integers, it will be cut out by this cutting plane. So this plane really cuts out, throws away the solution in which the variables are not integer. It's very cool, right? You have a constraint and then it automatically cuts out anything that is not integer. Any solution that is not integer, you are cutting that out. But then the solutions that are integer are not cut out by this problem. How do we know this? Well, if you see all the dots here, it is still covered in the area under the cutting plane. So all the dots, all the solutions that both values are integers, they are not thrown out. But the optimal solution to the LP relaxation, it is cut out already. The cutting plane can also be explained by looking at the equations. So just a quick review here. This is the second constraint. We see that the right-hand side is not integer, which in this problem is not allowed because you cannot produce table or chair with a quantity of 3.75. And then in the cutting plane algorithm, we're going to convert all the non-integers into this form. An integer, x in the bracket, plus the remaining fraction, f. So x in the bracket plus f. And then in this step, we group all the integer coefficients to the left and non-integer coefficients to the right. Finally, the cut constraint says that this right-hand side must be less than or equals to 0. Okay, now let's think about if this 3.75 had been integer, or in other words, let's suppose it is integer. It means that we will have something like this. So compare this and this. If the value had been integer, let's say 3.0, instead of having 0.75 here, we will have nothing, right? Because 3.0 is an integer, so 3 only belongs to the left-hand side and nothing on the right-hand side. Nothing means nothing on this part on the right-hand side, right? You have 0.75 here because your solution is 3.75 originally. Now suppose or assume that this is 3.0. So this is how it would look like. You have 3 on the right-hand side, but then you have nothing on this part. And then when you apply this constraint, saying that this entire right-hand side must be less than or equals to 0, this will be automatically satisfied. Why? Because S1 and S2 both must be larger than or equals to 0. So this right-hand side always satisfy this cut constraint. What I'm going to say is that if your solution is already integer, then it will always satisfy this cut constraint. However, if your solution's right-hand side is not integer, it will not satisfy the cut constraint, such that when you resolve the problem after adding the cut constraint, that solution will be cut out. Remember, like the optimal solution of the LP relaxation, it is thrown away, it is deleted, it is cut out by the cut constraint. However, all the other dots which are feasible solutions for the integer programming, they are not cut out by the cut constraint. So I think this cutting plane constraint is really something simple. You're just adding this constraint, but then it's actually really powerful and very smart. So that's the end of the integer programming topic. Basically, we have two big methods that are introduced in this chapter, the branch and bound method, and then the cutting plane algorithm. For the branch and bound method, we have seen that how we can apply that method into pure integer programming, mixed, and then 0-1 integer programming. And in this part, we've seen how we can use cutting plane algorithm and why it works. Okay, so as usual, if you have any question, feel free to go to IDE in the forum of Q&A and leave your questions there. And if there's any question there and you want to answer your friend's question, of course you can do it. Okay, thank you.